what he's going to talk about today. So his title today is Electronic Structure Information Concept, Method, Applications, and Plausible Extension. Please welcome Professor Sugimoto.
Thank you, Joe, for the for your kind introduction, even about the onsen. It was a very nice memory, and I'd like to express my sincere thanks to the organizers, including Joe, of course. And if I remember correctly, our first meeting was in the year of 2002 at the bilateral meeting between Korea and Japan, organized by the Institute for Molecular Science. Is this correct?
Yes.
Yes. So
I think so.
Now, so I'm very happy to know that Cheo is now a big professor in Korea, and he organizes a conference to encourage the human relationship all over the world. So this is quite a nice opportunity. But I'm really sorry to not joining the meeting in person. I'm now in Valencia, Spain, and to do some work on perovskite solar cell project. Anyway, today I'd like to talk about our recent research on electronic structure informatics. That is a field I'm suggesting in these days. And in this presentation, I'd like to explain what is electronic structure informatics and how we do it. How do we perform this? And I would like to show some applications recently we have made. And finally, I'd like to mention about the plausible extension. And the main purpose of this presentation is to contribute to the platform that Cheo is suggesting from the viewpoint of the applied quantum chemists. I've been working on the application of the quantum chemistry methods and to the variety of methods, as I will show you the next slide. This is because of my wonderful meeting with a lot of talented professors and researchers. I got the degree in Kyoto University, and I belonged to the same department as Professor Kenichi Fukui was, and my supervisor was Professor Hiroshi Nakatsuji. He's quite famous for the SAC-CI. Excuse me. And after finishing the PhD course, I was appointed with a company named Sumitomo Metals. And in this company days, I was quite lucky to engage in a variety of researches with computational methods, and the target materials semiconductors, dielectrics. So my field was quite expanded in these days during the year of 1993 to 1996. And after that, I was appointed as a lecturer in Kumamoto University since 1996. And even after my new position, I was quite happy to have a nice collaboration with Professor Susumu Kitagawa. He is quite famous for the porous coordination polymer, or MOF. And I was also invited to join a JST project for the energy carrier. In particular, our research topic was ammonia synthesis. And I was asked to do some computer simulations using Avincio MD to simulate how the catalytic reaction of ammonia synthesis proceeds. And also I was invited to join Professor Hiroshi Seiwa's project focusing on the NEDO perovskite solar cell. And now I'm in the second term of the NEDO project under the direction of Professor Hiroshi Seiwa. And this is quite also a very interesting opportunity. However, because of such careers, I have been working on a variety of research topics, as I'm showing on this slide. So on the basis of these experiences, I was so frustrated because I got a lot of criticism by the experimentalists, and what I like to. So that was my motivation why I'm proposing the electronic structure informatics. The idea is very simple. When we do the work on, when we try to develop functional materials, what is quite important is to establish, to discover, to find the structure property relationship, as I show on the slide. So, and the key point from the quantum chemist view is molecular structure is determined by the electronic wave function, as all of you know. And also the molecular property is also the function of the wave function. That's why from the quantum chemist view, electronic structure is a key information, and that is quite helpful to establish a relationship for the structure between structure and property. That's why about 10 years ago, I noticed this relationship. That's why I have been developing some kind of concepts named electronic structure informatics, and that is designed to establish the relationship via the information of the electronic structure. And so far, I have been working on the two types of applications of the quantum chemistry method. And I'm not on this in this presentation. I'd like to explain what about the second topic, electronic structure informatics. But before before thinking about this informatics method, I have been working on application of quantum chemistry methods for the models, systems, and I performed a lot of computations and analyzed the computed results very carefully, and I made suggestions. But all the time, experimenters says to me that why don't we suggest new molecules? But this is a very difficult task for quantum chemists because a molecular input is necessary to do the computation. So the direct prediction of the promising molecule is quite challenging. Therefore, I have now I am working on electronic structure informatics because this is good. This is nice to make suggestions about new molecules. I mean, I should say we can take advantage of the in silico screening. This slide summarizes my previous efforts in electronic structure simulations, and I've been working on solar cell, perovskite solar cell material. In this case, I have been working on the defect physics, and surface modification of the perovskite crystal was investigated in a research team. And recently, we are working on catalytic activities of nanoparticles on zeolites, as this movie shows. So these are also quite interesting, but I'm thinking we need to go beyond. In these days, I have just using the Matlantis software in which the quantum atomic forces are simulated by using the neural network algorithm. I mean, deep learning technology is used to simulate the DFT level calculations. And what my point I'm showing here is showing this here is such kind of say virtual experiment is also quite promising, even for my electronic structure informatics. And now I'd like to go to the discussion about electronic structure informatics. And at the beginning, the very say important concept for me was the concept suggested by Professor Rod Hochman, which is called isotope analogy. Professor Hochman suggested that when a chemical species have a very similar isolobal structure, I mean molecular orbital or shape, these two will show these two are expected to show the very similar chemical reactivity. I learned this many years ago when I was a student, PhD candidate, and when I think about when I thought about the in silico screening, I remember this. concept, and now in my strategy, I'm following his idea. And as you know, all the information important to for molecular science coming from the Schrödinger equation. And by looking at the Schrödinger equation, I can suggest three types of electronic structure informatics. That is the Hamiltonian-based electronic structure informatics. And there is an example I can suggest to you, and that is the model Hamiltonian approach. This is a kind of, say, projection of the complicated chemical system into the very simplified model Hamiltonian. And that is a way solid state physicists really loves. And the second type of ESI is a wave function-based informatics, electronic structure informatics. And typical example will be the frontier of the theory. And the third one is the topic I'd like to discuss today, and that is energy-based electronic structure informatics. Maybe all the participants in this meeting would be quantum chemists. That's why you can easily understand my point. As you know, when we try to do some analysis by using quantum chemistry methods, the most important parameter is the energy, because it decides it is quite important factor for the chemical reactivity. So knowing the shape topology of the potential energy surface is very critical, and this is the expression of the energy as a function of reaction coordinate. And so in order to develop the informatics method on the basis of quantum chemistry, my original idea was to use the mathematical relationship suggested by the people working in the electron transfer theory. In the year of 2000, I was a visiting researcher at the Brookhaven National Laboratory, New York. And at the time, my supervisor was Marshall Newton, and I learned a lot from him about the electron transfer theory. And at that time, of course, most of you know the very classical electron transfer theory developed by Professor Rudy Marcus suggests that the activation energy for the chemical reaction or electron transfer reaction can be represented in this very simple formula. Here, the delta G0 is the driving force of the chemical reaction, and the lambda is the reorganization energy, defined it like this. And this energy is the energy difference between this point and this point. And this point corresponds to the geometry equal to the equilibrium structure of the ground state of the reactant. And by performing the quantum chemistry calculation to get the energy of this point and this point, and we can easily evaluate the reorganization energy lambda. And we have been showing this parameter is quite important for the chemical reaction, as well as the whole transport properties in the whole transport materials applied to, for example, the OLED system or the solar cell. Therefore, I'm thinking these two parameters are quite important. And when we think about some sort of chemical reactions with a specific target molecule, just like a protein, and we can think that the lambda of the ligand would be critically important. Therefore, even in the ligand-based drug design, we can take advantage of this relation. My point here is we can skip the evaluation of the activation energy by using this equation. Of course, this is a model, but it can be it can be considered as a nice measure for the reactivity. And when we think about the energy changes, because I was a student of Professor Nakatsuji, who developed the SAC-CI method, I thought that we should focus on a variety of electronic structure electronic state, because when I go back to this slide, this view graph says that the both ground state and excited states participate in the chemical reaction. That's why we should not limit ourselves only to the ground state. We should also focus on the excited state information. That's why in my informatics method, I'm focusing on the excited states, singlet excited states, as well the lowest spin triplet state, T1 state, and in many situations, just like a nucleophilic attack or the electrophilic attack, we need to mind about the charge transfer. Therefore, in my approach, I'm also taking into account the ionized states as well as an anion state. We evaluate the ionization potentials on the electron affinity by applying the delta SCF method for these three states. Also, in my informatics, I'm trying to include some sort of the information that can be related to molecular properties. This is a copy of my very first paper under the supervision of Professor Hiroshi Nakatsuji. This was a study on the metal enamel chemical shift. Enamel chemical shift is a difference between the magnetic shielding constant that is a second order perturbation property of molecules. And as you know, the second order properties can be mathematically expressed by using the sum over states formula given like this. So that this means that the molecular property, when we are interested, when we focus on a particular molecular property represented in the perturbation expansion of the energy, we should mind that excited states also participate to the molecular property. That's why in my informatics, I'm applying the TDDFT calculation to evaluate the excitation energy, and the matrix element is also taken into account in my informatics. This is a very unique feature of my informatics in comparison with the other previously developed chemoinformatics method. This slide indicates that even for the van der Waals interaction is represented by using the second order perturbation theory. Therefore, I'm thinking I think that in order to take into account in order to express the intermolecular interaction via van der Waals interaction, this equation says that we should mind about the information related to excited states. And the third type of descriptors representation of the molecule we are taking into account is a molecular shape. One parameter is a molecular volume, but molecular volume represents the isotropic characteristics of the molecule. So when the target molecule have a very large anisotropy, we should mind about the anisotropy of the molecules. That because of this, we are now introducing such kind of rectangle that enclose the target molecule, and the three parameters represented here, represented as B1, B2, B3 here, also taken into account as an important information of the for molecules. As you know, the such kind of size parameters reflect the topology of the potential energy curve. Because of this, I'm thinking that these parameters, I mean volume or B1, B2, B3, may be considered as a description of the energy between two molecules. And the fourth type of description I'm taking into account is the changes in the solvation environment. And this was motivated in my previous experiences focusing on metal ion selectivity in polymer resin. That one is a functional group capturing the metal ion, and one colleague in my department encouraged me to evaluate the to predict the metal ion selectivity in organic resin. At the time, I simply at the beginning, I took only the functional group and metal ion interaction, but the quantum chemistry calculation evaluating the binding energy between two completely disagree with the experiment. And because of this disagreement, I noticed that desolvation process to migrate into the polymer resin would be very important factor. Therefore, this may be very similar in a biochemical situation. For example, if M may be considered as can be considered as a drug molecule, this should be desolvated when it goes into the membrane. Therefore, I'm now taking into account the desolvation energy that is, in my case, evaluated by using the PCM, polarizable continuum model, in the Gaussian 16. And this is a summary of the types of the descriptors I'm using for my electronic structure informatics. And by using the four types of parameters, what I'm doing is to develop the machine learning model by using, for example, support vector machine or random forest, or recently we are applying the XGBoost by using these descriptors. This table summarizes the descriptors we are using, and basically the 20 parameters were evaluated after quantum chemistry calculations. We also add one additional descriptor, molecular weight or molecular mass, and this is to take into account the transport property of the molecule. And this parameter is frequently included in chemoinformatics and QSA, quantitative structure activity relationship studies. Therefore, this is a kind of intuition-based introduction of the descriptor. Anyway, the parameter descriptors we are using for the machine learning is only 21, and this is quite small in number in comparison with the other chemoinformatics software, just like AlbaDesk. AlbaDesk has descriptors more than 5,000, and of course this is expected to be good. But if we focus on a very small data set, small sized descriptor set would be nice in order to avoid the overfitting in machine learning. Time is almost running out, so let me go quickly to introduce applications. This is this graph represent how good our prediction was by using our electronic structure informatics descriptors and random forest. Horizontal axis represent the predicted value for the IC50. In this case, we focus on inhibitors against the fatty acid synthase enzyme. And these compounds are considered to be a nice anti-cancer drug because this enzyme contributes to accelerate the growth of the cancer cell. And the second application was done to the microbial reagent, and this shows the strategy would be useful even for this case. And another, also we did the in silico screening by focusing on the natural product database. And third type of the application was about the toxicity prediction, and this is the toxicity prediction of the phenol derivative, and the horizontal axis indicates the toxicity of the predicted toxicity of the phenol derivatives. And as you see, the correlation between the experimental and predicted value was so nice. And this noisy table represents the application of the ESI descriptors with XGBoost classifier. In the literature, we could find the experimentalists classification of the mode of action or mechanism of the toxic action. And the numbers here are represent the number of molecules. And for the mechanism named polar narcotic, experimentalists assigned 174 molecules. And we used 139 molecules for the training in the machine learning, and we checked the accuracy of our machine learning model for the 35 molecules. And we did the same thing for all the molecules included in each of 5 MOA classes. And our prediction was quite good to reproduce the experimental classification. We have been applying our descriptor set and machine learning standard machine learning methods to a variety of say phenomena or properties, this is a kind of empirical approach. Therefore, we need to apply our methods to more cases. But so far, we may say that our ESI descriptors works quite well. And what we are doing is just like identifying what is elephant by using the different hands. I mean, here are 6 eye handicapped people are shown on the slide, and each person touches the same elephant, but the view will be very different. This was a previous situation in computational chemistry. Computational chemist discusses the shape of the elephant by the local description, but the chemoinformatician do the same thing in a different part, and the experimenters do the same thing in a different part, and their conclusion may be different. But by applying the plural number of scientific methods, we will certainly identify what this elephant is very correctly. Therefore, application of the informatics method is also quite important if the data is based on the quantum chemistry. And in this presentation, I suggested application of the energy-based ESI. And the possible extension would be to apply the robotics in future, and the simulation technologies, in particular, MD simulation would play a key role, in particular in condensed matters. And finally, I'd like to suggest that we computational chemists can contribute to make a lot of Superman for chemistry, because we have a key technologies for the AIs and the robotics, because we can do programming. But of course, we should remember that in order to make this real, we need to develop a very nice, fancy platform which combines a variety of tools like a database or the machine learning tools. Therefore, Charles' suggestion about this meeting is quite nice, because this would be a nice motivator for the future development, combining a variety of computational methods. This is the final slide I'd like to show, and I really appreciate my students for their hard working, and also the fund and the grants. I'm showing this in this part. And finally, I'd like to appreciate your kind attention, and I would be happy to have some question, but I'm really sorry. I used up my time.